All right, this is Thursday, April 1st, 2021, Aerospace Engineering. Mr. Turek, trying to teach students today how to do a Hoffman transfer, a basic orbital mechanics skill as far as I'm concerned. So we have a central body, could be the Earth. Let's use the Earth as a fine example for right now. And the very first skill you have to be able to do is to calculate all about a circular orbit around the Earth. So let's just practice that skill once. There's the radius of the Earth, capital R, and in the case of planet Earth, I've memorized it, right? 6,378 kilometers. And this is the average radius of the Earth using my favorite computer program, STK. So I just want to be consistent with that program. Then separately, we can have the altitude above the surface of the Earth. And I'm just using the Earth as our main example. Of course, the central bodies I care about the most in my own research are the Earth, the Moon, and Mars. Then there's finally the orbit radius, which, if you need to calculate it from these two parameters, it would be the sum of the radius of the Earth plus the altitude above the surface of the Earth. Those two added together will give you the orbit radius. The formulas that we use for relating orbital period, orbital speed, orbital radius to each other, the main one would be Newton's version of Kepler's third law. T squared equals 4 pi squared r cubed over g over m, where g is the universal gravitational constant and m is the mass of whatever body that we're orbiting. Little reminder, you should have this in your calculator memory. G is equal to 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared. In the case of the Earth, the mass is 5.974 times 10 to the 24th power kilograms. By the way, some of you on your homework calculations, even though you're normally top students, you use slightly incorrect values like 5.79 instead of 5.97. So that could explain why you lost at least a point on your homework. Something to watch out for. Of course, the orbital period has to be expressed in units of seconds, and the orbit radius in units of meters. Otherwise, things go kablooey. The other parameter or equation that we use for a circular orbit is the orbital speed squared is the product of the universal gravitational constant g times the mass of the central body divided by the orbit radius r. And v here is orbital. I could call it velocity, but I'll just write speed today. Orbital speed in units of meters per second. So just as a trivial example, let's say that I have a satellite orbiting the Earth. Okay, so I just asked my students for an example problem, and they suggested, how about an orbital radius of 25,000 kilometers? So I can tell you this is a pretty far out from the Earth. The Earth is only 6,300 kilometers in radius, 6,400. So this is, significantly up there in space. But calculate, please, as an exercise, what would be, I'll tell you what, we don't need to calculate the orbital period in this situation. we'll just calculate what we need to learn about Hoffman transfers. So all we need to know is the orbital radius. So if we didn't have that, if we were given the altitude instead, we'd have to solve to get the orbit radius. If we had been given the period instead, we would have had to have solved for the orbit radius. But as luck would have it, the student gave us the orbital radius to start off with, and that's what we need. The other thing that we need is the orbital speed. So calculate, please, for this situation of a satellite in a circular orbit orbiting the Earth with the orbit radius of 25,000 kilometers, what would be the value of the orbital speed? Calculate, please. Okay, my students and I agree that the answer that we get in this situation is 3,993 meters per second. So we need that number, 3,993 meters per second. Now, we're going to create a problem of saying we're in this circular orbit. We're zipping along at nearly 4 kilometers per second. So we're going, I forget the conversions, but you're going fast, right? You're going more than 2 miles per second. And that's fine. And you're going to stay there forever if there's no friction. Another part of aerospace engineering, if you get into it, is well, there is friction. So there's an orbital lifetime, and it's affected by the solar cycle, which varies every 11 years. But at 25,000 kilometers, the orbital lifetime is going to be measured in centuries already. Okay, not hours, days, weeks, months, or years, but hundreds and hundreds of years at a time. Now, let's do the same thing a second time and say, okay, here's the Earth. And I'm very far away from the Earth in this case. I might be visiting a solar power satellite, but probably not, because this isn't really where we plan to put them. There might be some sort of infrastructure up here, but we want to go someplace else. Maybe we want to go to geosynchronous orbit. That's not too far away, and it's a very popular place for communication satellites. Maybe we want to drop down to a GPS orbit, which is about a 12-hour orbital period around the Earth. So I need a second circular orbit that will be the destination for this example. All right, so the second orbit, which I'm going to have to draw as being closer to, well, this was never to scale anyways, right? 25,000 kilometers would be like 4 diameters out. So I will draw the second orbit not to scale, and the student generated value was, let's go to an orbit radius, again, that saves time, of 10,000 kilometers. So in this case, calculate once again the two things that we need to know, orbit radius and orbital speed. So being given orbit radius, calculate please, what is the orbital speed? Okay, my students and I agree that we get 6,313 meters per second. And I know I should only do this to 3 sig figs normally, but I do have this inappropriate habit of carrying out time to the second and velocity to the meter per second, even though I should not. All right, so in Project Lead the Way, they have you calculate how much energy you have in this circular orbit, and there's a formula for that. Something like the total energy is negative gm little m, maybe over 2r for a circular orbit. I think that's it. And so you could calculate the energy in this last orbit, the energy in the first orbit. You would discover that the energy in the first orbit is greater than the energy in this second orbit, and therefore you have to lose energy to drop down closer to the surface of the Earth. And you get some answer in joules. But we're interested in building rockets that go into space and and do things like this maneuver. And it's not so much a question of how much energy, it becomes a question of how much rocket fuel would you need to do this job. And I think that's just a little bit beyond what I can teach you today. But what I can teach you today is how to calculate the change in velocity that you would need to go from one orbit to the other. So I'm going to change my scale here a little bit and say, here's the Earth now. And 10,000 kilometers might be something sort of like that. If you can imagine that's a circle, I know I missed my target there, right? I should have drawn something that looks more like that. Oh well, too bad we can't ignore this. Maybe I should just start over. Here's the Earth. Let me see if I can do a decent circle. There, a deflated tire circle. And then the first orbit was like 4 diameters out, right? 1, 2, 3, 4. So that was like going from here down to there. So here's our 25,000 kilometer orbit, closer to being to scale. Here's our 10,000 kilometer orbit, a little bit closer to being to scale. And how do you go if you start here and you want to end up there? Hence the title of today's lecture. There was a German engineer in the 1920s or so who analyzed what is the least energy, what is the most energy efficient way to transfer from one circular orbit to another circular orbit around the same central body. And his last name was Hohmann. So we call it a Hohmann transfer orbit. And what you do is you build an elliptical orbit. This elliptical orbit has to just barely touch both of the circular orbits. So I usually draw it as starting here and then an ellipse that goes out and touches just there. And really, that's half an ellipse. If I were to draw the rest of the ellipse, it would come down. Okay, so I'm going to draw just half the ellipse. So this is the transfer orbit. Now, sadly, things are starting to get complicated. We need to calculate the properties of this elliptical orbit. And it's true, I've given a couple of problems for you to do it, but let's review, all the details of calculating an elliptical orbit. So I'm going to draw just half of an ellipse. And what makes this thing more of an ellipse is that it's not a circle, it's like a squished circle. And let's say that here is where my central body is. So I'm going to draw just half the central body. Maybe I shouldn't do that, right? So there's our central body. The distance from the closest point in the elliptical orbit to the central body is called periapsis. So from here to there is called the periapsis radius. The distance from the farthest point in this elliptical orbit to the central body, so from here to the center of that is called apoapsis. Peri means near, Apo means far. So nearest point, farthest point. And in the special case, when the central body happens to be the Earth, then we change the apsis name and call it perigee, G for Earth, and of course, apogee, G for Earth. So special case, this means Earth as the central body. On an elliptical orbit, you go faster when you're closer and you go slower when you're farther away. To calculate those speeds, here's what I say. It's useful to calculate the average distance. And that average distance, so what do? The total distance, if you add the two distances together, the periapsis and the apoapsis, that is called the major axis of this, that's J, major axis of this ellipse. Half of that would be called the semi-major axis. And we represent the semi-major axis with lowercase letter a. Okay, so how do we get the value of the semi-major axis? Well, 2 times a is equal to the periapsis distance plus the apoapsis distance. 2a equals our peri plus our apo. Well, I can solve for a by dividing both sides by 2. So the semi-major axis is the periapsis distance, radius, and the apoapsis radius divided by 2. In this example, the semi-major axis would be 10,000 kilometers plus 25,000 kilometers divided by 2. Well, 35 divided by 2 should be 17.4, unless I'm getting too old for this. 35 divided by 2 is, I'm 0.5, I should say. So 17,500 kilometers is the value of the semi-major axis in this example that we're creating. So really, this is page 2, and this is what we have so far. Okay, so I am blitzing along at ludicrous speed, getting us to become masters of doing Hohmann orbit transfer calculations this period. We're almost at the halfway point in this period, but let me keep going. Anyways, I'm on a roll. So the next part of this is to say this average distance, because that's what it is, it's the average value of these two numbers, is the average velocity for this elliptical orbit. And so we can calculate using that same formula as before, v squared equals g times m divided by r. We can calculate v squared equals g times m divided by a, where a is the semi-major axis. But of course, every time we do our calculations, we have to put it in units of meters. So calculate, please, what is the average orbital velocity of this elliptical orbit? All right, so following a break and several attempts, students say the average velocity, and I agree, is 4,772 meters per second. Great, but we're also interested, so for this elliptical orbit, we really need 4 pieces of information. We need to know here, for this elliptical orbit, we need to know the semi-major axis. We need to know the excuse me, average velocity. We need to know the orbital period. We haven't calculated that yet. Later, we'll need to calculate the periapsis velocity and the apoapsis velocity. So far, we have the semi-major axis is 17,500 kilometers. We just calculated the average orbital velocity is 4,772 meters per second, but we're going to eventually want to know what is the orbital period for this elliptical orbit. And the beauty is we use the semi-major axis to find that answer. So we're going to plug it into the previous equation, t squared equals 4 pi squared r cubed over gm, but instead of r for a circular orbit, we're just going to substitute in a for an elliptical orbit. So calculate, please. In units of seconds will be fine. How many seconds does it take for a satellite on this elliptical orbit to complete one revolution around the Earth? Calculate, please. Okay, so the situation here is you're going to solve for t. So if you take the square root of both sides, then the 4 squared becomes, I'm sorry, the 4 becomes 2 squared. The square root of 4 is 2. The square root of pi squared is pi. And then you're going to take the square root of the semi-major axis cubed after you turn this into meters. So it's going to be 17,500,000 meters. And then finish it off underneath the square root sign. You're still dividing by g, and you're still dividing by the mass of the Earth. Now, if you want, you can put parentheses surrounding the g and the m on your calculator. But if you don't bother with the parentheses, then underneath the square root sign, you're going to have to do the 17,500,000 cubed divided by g divided by m. And sadly, this one is turning out to be too challenging for my students, for the majority of them to get it. But the way you should solve for it would be to say square root of 4 is 2, square root of pi squared is pi, so 2 pi times the square root of, put in the semi-major axis in units of meters, so 17,500 kilometers becomes 17,500,000 meters cubed. Then divide that by the universal gravitational constant g, which I've stored in my calculator memory, and divide it by the mass of the Earth, all underneath the square root symbol. As you can see, I get 23,040 seconds of time. And if you're curious, what is that? Well, divided by 60, that's 384 minutes. If you're curious, divide that by 60, and that means 6.4 hours. Kind of a reasonable number based on experience of doing this stuff many, many times. Okay, so a little disappointing that only 1 out of 5 students calculated that value correctly. Oh man. Here's the formula, right? T squared equals 4 pi squared r cubed over gm becomes t is equal to 2 pi square root of a cubed over gm. But wait, there's more. We need to calculate the periapsis velocity and the apoapsis velocity. Well, the formula for doing that periapsis velocity is equal to the average orbital velocity, which is why we needed to calculate it, times the square root of, now keep in mind, we're going faster as we get closer to the Earth. So we're looking at this part of the elliptical orbit. You zoom closer to the Earth, you speed up because gravity is pulling you towards the Earth. You slow down as you go away from the Earth. You're going uphill against the pull of Earth's gravity. Speed up, slow down, speed up, slow down, speed up. So, keeping that in mind, you expect to get an answer here that is above average value for speed, and an answer up here that is below average in speed. I point this out to you because in this formula, students often do it wrong. What goes in here is the square root of the apoapsis radius divided by the periapsis radius. Now think about that for a moment. Apo is the far away one, peri is the near one, so this becomes a number greater than 1. You're taking the square root of a number greater than 1, which becomes a number still greater than 1. And that means the periapsis velocity is going to be above average. To me, that should be like super obvious. So in this situation, you should calculate what is the product of the average orbital speed of 4,772 meters per second times the square root of the apoapsis radius of 25,000 kilometers divided by the periapsis radius of 10,000 kilometers. And you can get rid of 3 of those zeros. You could just say, what is the square root of 25 divided by 10? You could even get rid of one more decimal and say, what is the square root of 2.5 times the average velocity? All right, calculate, please. What is the periapsis velocity? Okay, since I put the value in my calculator rounded to the nearest meter per second, over here, my student and I disagree to the last digit, but that's not significant in the real world. So 7,545 or 6 meters per second, and that is above average. To calculate the apoapsis velocity, it is the product of the average orbital speed times the square root of, you flip these two over. So you put the r peri in the numerator, you put the r apo in the denominator. This is a number smaller than 1. The square root of a number smaller than 1 is a number smaller than 1. So the apoapsis velocity is going to be below the average velocity. Calculate, please. Oh, and by the way, since this is the reciprocal of that, you could just say this is the average orbital velocity divided by this first ratio. So instead of multiplying it by the square root of 2.5, you could say I'm dividing it by the square root of 2.5, and that'll give you the same answer. Calculate, please. Okay, my students and I agree that the answer we get in this situation is 3,018 meters per second. We're now armed with all the information we need to actually do a Hohmann orbit transfer. So let me go back to this diagram and talk you through it. Actually, I like this diagram. So we're starting off going at this large orbit, 25,000 kilometers radius. And we had already calculated in the previous episode that we had the orbital speed up here in this larger orbit. Some piece of information that I have on the page underneath this one. No, it's not even on that page. Did I not write it down? Oh, yeah, I wrote it down. Okay, so we're starting off at a speed of 3,993 meters per second up here. I'm going to copy that over. Our speed up here is 3,993 meters per second. And down here at 10,000 kilometers altitude, our speed was 6,313 meters per second. Now, if this were on a straight line on the surface of the Earth, you would say, oh, here I'm going slower than I'm going there. So to change from this speed to that speed, I need to speed up and go faster. But the amazing but true feature of orbital mechanics is if you want to end up going at this faster speed, the first thing you're going to have to do is slow down. I'm not making this up. And then later on, you're going to have to slow down again. And after you slow down twice, then you'll be going faster than when you started. Amazing and true. Here's how that works. You're going along in this outer orbit at this circular orbit velocity. Where it just touches the top of the elliptical orbit, we just calculated that at the top of this elliptical orbit, you would have to be going at 3,018 meters per second if you were going to be on this elliptical orbit. So if you look carefully at these two numbers, you're zipping along in a circle at 3,993 meters per second, but to drop down closer to the Earth, you need to slow down to 3,018 meters per second. And we refer to this as delta V. What is my change in velocity? Well, this first change in velocity, because we're going to have to do two of them, in this geometry is going to be the velocity at apogee minus the velocity of our outer orbit, I guess I'll call it. And that means in this situation, mathematically, we are doing our 3,993 meters per second, 3,993 meters per second. And now we need to, change it so that we're only going at 3,018 meters per second. And I see I wrote it incorrectly. Sorry, these two numbers should be switched around. It's really 3,018 meters per second minus 3,993 meters per second. So this is your initial velocity, And this is your final velocity as far as this change in velocity goes. I mean, this part is always true. Change in position, change in velocity, change in acceleration is defined as final state minus initial state, always in that order. So I want to end up going slower than I start. So this is going to be a negative change. And I'll just do it on my calculator. 993 minus 18 means my change is really negative 975 meters per second. If I'm going along on my circular orbit and I slow down, I will now be at the top of this elliptical orbit. And I will start falling towards the Earth, speeding up as I go downhill, racing faster and faster and faster. Okay, well, when I get down to the closest point to the Earth, I will just start going uphill again and slowing down. Slow down, speed up, slow down, speed up, slow down, speed up, forever, ignoring friction. But I don't want to just stay on this elliptical orbit. I want it to end up in the circular orbit. So let's zoom in, figuratively, at the moment when I'm at the bottom of this elliptical orbit. Well, I'll be going pretty darn fast. 7,545 meters per second, we calculated. But the 10,000 kilometer radius circular orbit is not going that fast. It's only going at 6,313 meters per second. I'm going too fast to stay in this circular orbit around the Earth. I need to slow down. By how much, you ask? Well, change in state is defined as your final state minus your initial state. So here, our final state is the velocity of the inner circular orbit, and our initial state is the periapsis velocity at the near point of that elliptical orbit. The numbers that we would plug in this situation would be the velocity at the 10,000 kilometer altitude orbit, which we said is 6,313 meters per second, and subtract from that the periapsis velocity of 7,545 meters per second. So before I turn on my calculator and tell you the answer, I want to point out that the two changes in velocity are not going to have the same value. The inner change will be larger in magnitude than the outer change. And the greater the ratio of the orbits, the, uh, the less closer to being equal these two values will be. So don't just say, oh, let's just double the previous value of negative 975 meters per second. That won't be large enough in this case. So if I go on my calculator and I ask it, what is 6313 minus 7545? I'm expecting an answer greater than negative, in magnitude, greater than 975. And sure enough, the answer is the second change in velocity is going to be negative 1,232 meters per second. We're almost done. For a Hohmann transfer, there are three pieces of information that we care about. Nah, maybe I should say two. What is the total change in velocity that we need? And what is the time of flight, abbreviated just TOF, to execute this maneuver? Well, the total change in velocity is the sum of the two individual changes in velocity. So in this example, if I take negative 1232 and subtract from that 975, my total change in velocity is negative 2,207 meters per second. To get the time of flight, maybe you can understand why I only drew half an ellipse. The time of flight from the first delta V to the second delta V is 1/2 of the orbital period. So if we take the period for the elliptical transfer orbit and divide it by 2, that is the answer from me to you. All right, well, the time of flight was, the orbital period was 23,040 seconds. So if I divide that number by 2, my calculator says the time of flight is 11,520 seconds. And if you're curious, divide that by 60, and it says that's 192 minutes. And if that's still not good enough for you, you could say that is 3.2 hours. And that is precisely the time between the two delta V's. So there's one final comment I'm going to make about all this is, what do you do with these two answers? What do you do with the total delta V? What do you do with the time of flight? And the answer is the rocket equation. Armed with this information in particular, now you can calculate how much rocket fuel you need to expend to execute this transfer. There's only 2 minutes left in the period. I am not going to teach you the rocket equation 2 minutes before the start of spring break. But I will say this is on our reference sheet that I provided to students. And it depends on your choice of rocket fuel. Historically, we've been using liquid hydrogen, liquid oxygen. SpaceX is moving towards using methane oxygen because methane can be produced from the atmosphere of Mars. So if you want to fly to Mars and refuel your rocket while you're on Mars, it's easier to get a hold of methane through a chemical process than it is to get a hold of hydrogen. Because at the time that we started researching this, we weren't certain that we could find water on Mars. And if we did find it, could we really convert it into hydrogen and oxygen without violating the scientific uses of finding that water? So I'm stopping here. This is what I consider to be very logical, fun part of orbital mechanics, you might want to challenge yourselves to use STK to model this. And the part of STK that really lets you do stuff like this is called the astrogator. And they even have a tutorial in there called a Hoffman transfer. You could do the tutorial, and if you want, for fun, put in today's example that we did in class and see for yourself how much rocket fuel it would take.